Hello all. The size of an object depends upon the distance of viewing. When we view an object from a closer distance, it appears bigger in size. But when the same object is viewed from a longer distance, it appears smaller in size. In order to view an object uh, to in a big size, we have to bring that object close to our eyes. As we bring the object closer to our eye, it appears bigger and bigger. The size of an object as we perceive it, depending upon its distance, is called apparent size. The true size always remains same, whichever distance an object is present. But the size as we perceive it, when it is closer it appears bigger, when it is further away it appears smaller. The size as we perceive it is called an apparent size. In order to view an object bigger and bigger, we have to bring it closer and closer to our eyes. But how close can we bring an object to our eyes? There is some limit. If an object is too close to our eyes, it appears blurred, not clear. Sometimes we have to strain our eyes in order to see the object clearly. An object can be seen clearly at a minimum distance of 25 centimeter. If the object is closer than 25 centimeter, it will not appear clear. So the minimum distance of an object for it to be clearly visible is 25 centimeter. It is for normal human eye, adult eye. This minimum distance for clear vision of an object may vary depending upon the condition of eyes and the age of human being. For a normal adult human being, this distance of clear vision, minimum distance of clear vision or a minimum distance of distinct vision, it is 25 centimeter. It is also called near point. Now, as already mentioned, an object that is further away appears smaller in size. An object, when it is closer, it appears bigger in size. Here I have shown in the diagram, this first diagram. The true size of 3 remains same. However, at a longer distance of d2, the size of the 3 appear as shown here. So what we see here is that the apparent size of an object depends directly upon the angle subtended at our eyes. Here we have drawn light rays from top and bottom of a tree. These light rays upon meeting on our retina makes an angle of θ1. This angle is the angle subtended by the light rays. It is upon this angle subtended at our retina the size of an object depends. Greater the angle subtended, greater will be the size of an object. Lesser the angle subtended, lesser will be the size of an object as we perceive it, the apparent size. So, at a distance d1 as shown here, the angle subtended θ1 is greater than the angle subtended θ2 at a longer distance of d2. So, when the distance is longer, less angle is subtended, and we see the apparent size of an object decreases. When the angle subtended is greater, the apparent size of an object increases. So, the apparent size of an object depends directly upon angle subtended. With the increase in distance, the apparent size decreases. With decrease in the distance, apparent size increases. But the apparent size has a direct relationship with the angle subtended at our eye. Greater the angle subtended, greater will be the apparent size. Lesser the angle subtended, lesser will be the apparent size. So as compared to this size, this apparent size of a 3, the apparent size of a 3 we perceive at a longer distance of d2 is this. What if an object is too small to be clearly visible? We know that when an object is brought closer to our eyes, the apparent size increases. So when we have to view a very small object, we might expect bringing it closer to our eyes in order to see it clearly, expecting that the size of a smaller object will increase as it is brought closer and closer to our eye. But if you bring the object too close to your eyes, it appears blurred. Instead of enlarging in size, it appears blurred, and we have to strain our eyes sometime to see it clearly. So, to view very small objects, we cannot expect it to bring close to our eyes and see an enlarged view of that object. So, to be able to see a small object by enlarging its size in some way. Bringing it closer to our eyes is not a solution, but the solution is available with the help of a lens. When the lens is placed in front of our eye, then a tiny object can be enlarged. The enlarged image of tiny object can be formed, and we will be able to see the minute features of an object over the small object itself. The device we use for creating enlarged images of small objects is known as microscope. So you may have seen microscope in science laboratories. What do they do? Especially they are used for viewing the objects as small as the cells of our body. The cells are too small to be visible. However, when they are placed below microscope, the size of the cells is enlarged, it is magnified, and we can see we can look into the interior of these cells. As I have already said, we can increase the apparent size of an object by bringing it closer and closer to our eyes, but there is a certain limit up to how close it can be brought to our eyes. If we bring an object closer than the distance of 25 centimeter, then it will not appear clear, it will appear blurred. So the maximum apparent size of an object occur at a distance of 25 centimeter. So it is at a distance of 25 centimeters that we can have a clear vision as well as maximum or enlarged view of an object. In the diagram we have shown an object that is brought at a distance of 25 centimeter, and we have a clear vision and enlarged view or the maximum apparent size of this object at this distance. Angle subtended is theta 0. Now suppose if an object is already very small to be clearly visible even at this distance of 25 centimeter, and if you hope to view an object by enlarging, by causing the apparent size of it to increase by bringing it still closer than 25 centimeter, then it will not work. That object will not appear clear when we bring it closer than 25 centimeter, because that is the minimum distance of distinct vision. So the maximum enlargement or maximum magnification in the apparent size, maximum apparent size of an object is achieved only up to the distance of 25 centimeter. But if the object is already small and we want to view the enlarged image of it, we need a microscope. We are going to talk about a simple microscope that consists of a single converging lens as shown here in the diagram. This is a simple microscope. It is also called magnifier. It directly produces enlarged image of tiny objects. For example, on map, we can enlarge the images of tiny words on the map and are able to read those tiny words on map by using this magnifier. Maximum apparent size occur at a distance of 25 centimeter. Now we place a magnifier in front of our eye. It will produce an enlarged image of an object, and we will be able to view enlarged images of tiny objects. This is a converging lens, and this is an principal axis. This is the focal point, and the focal length of converging lens is small f. An object is placed a little beyond the focal point. The size of an object is h, and its distance from the optical center of lens is u. This is called an object distance. A light ray from top of an object, two light rays from top of an object. One light ray parallel to principal axis, another light ray passing directly through the optical center of the lens. We know that a light ray parallel to the principal axis will cut the principal axis at a focal point, while the light ray passing through the optical center of the lens, it passed through the lens and deviated. And we are viewing from this side of a lens. Now we extend these light rays backward. When the light rays after refraction through a lens are produced backward, we see that they meet at this point. So when we view from this position, the light rays appear to come from this point rather than from the top point of an object. The light rays are appearing to arrive to our eyes from this point. So the image of the top of an object is produced here. By using similar construction, it can be shown that the image of the bottom is produced on the principal axis itself. So this is the bottom image of an object and this is the image of top of an object. And we see that the image has a larger size than an object. And this is how this converging lens produces enlarged image of smaller object. And thus by use of the converging lens, we can produce magnified images of tiny objects and can view those tiny objects. Or if we are interested in viewing the minute features of an object, then minute features of an object are also magnified by using converging lens. We know that in order to produce enlarged image of an object or in order to increase the apparent size of an object, it must be brought closer to our eye. What we have done? We have really brought this object closer to our eye. The object is now closer to our eye than the distance of 25 centimeter. But now the light rays are refracted on passing through the converging lens. And upon refraction, the light rays appear to come from this point rather than the top of an object. So what we view or what we see is not an object, but its image. And the image has formed sufficiently far away from our eye so that we can view it clearly without having to strain our eyes. So what we see here, that the angle subtended at our eye is larger than the angle subtended without lens for the closest distance of distant vision. With this angle, here we have achieved greater angle to be subtended at our eye and hence view the enlarged image of an object. At this point, we define angular magnification. Converging lens allows, what converging lens does? Converging lens allows an object to be brought closer to our eye in order to increase the angle subtended and hence be able to view the magnified image of an object. We define angular magnification as the ratio of the angle subtended at our eyes with the converging lens present and the angle subtended at our eye with the absence of converging lens. This is the magnification ratio, the ratio of angle subtended at our eye with the lens present and angle subtended at our eye when an object is at a closest distance of distinct vision, which is theta 0. We can obtain angular magnification by substituting for the values of theta and theta 0. But the values theta and theta 0 cannot be directly measured. So we hope to express this formula in terms of the quantities which can be easily measured in experiments. For that, we will have to do some observation. Little geometrical observation will help us put this formula in a form that will enable us to calculate magnification experimentally. We assume that these angles are very small and therefore using small angle approximation we can write theta 0 as tan theta 0 and tan theta 0 applied to this triangle, the ratio of opposite side which is h to the adjacent side which is d. So we have theta 0 equal to h upon d. D is the near point, which is simply 25 centimeter. Similarly, we look at this triangle with the lens present. Here we can write theta approximately equal to tan theta, and we apply uh, tan theta to this triangle A, B and C. In this triangle ABC, angle B is 90 degree, and therefore this angle is also theta, this angle is also theta, and therefore tan theta may be written as the ratio of opposite side, which is H, upon the adjacent side is U. However, the object distance is negative according to sign convention, but the side of the triangle is positive. So we will have to add a negative sign here to make the denominator positive, giving the side of an adjacent triangle. So this is how we obtain tan theta equal to H upon minus U. Now we substitute for theta and theta 0 according to this equation into the formula for magnification, and we obtain magnification equal to negative D upon U. Now we use thin lens equation. This is the thin lens equation. 1 upon U equal 1 upon V minus 1 upon F. V is the image distance, F is the focal length of the lens, and U is the object distance. We substitute for 1 by U as 1 by V minus 1 by F in this equation. Before we substitute for 1 by V, 1 by U, we consider the case of near point, the image formed at a near point. So when image is formed at a near point, the image distance will be negative D according to sign convention. Image can form anywhere, but even image should not be closer than 25 centimeter. Again, the image will not be visible clearly. So minimum distance of image from the lens must again be the near point distance, that is the 25 centimeter. So we first consider the case of image formed at a near point, that is at a distance of 25 centimeter from the lens. So image distance is 25 centimeter. Following sign convention, we take image distance to be negative 25 centimeter. Instead of directly using the value of 25 centimeter, we prefer to write negative D, because the value of D, the near point, vary depending upon the person who views it and the condition of his eyes. Now, the image that we obtain in this setting is the virtual, upright and magnified image. For these image features, our object must be closer than the focal point to the lens. It must be closer than the focal point to the lens, and that is what we have done here. However, to get image at a distance of near point, the object distance must be properly adjusted, because the nature of image, the distance of image depends upon the distance of object from the lens. So using this lens equation, we find the distance of an object from the lens for which the image is formed at a near point. We substitute for the image distance in the thin lens formula and obtain the appropriate object distance for the image at a near point. On substitution for V equal to negative D in this equation, we get this equation. And now we replace 1 by U from this expression by this expression, and we get negative. We first multiply both the side by D, so that on the left hand side we get negative D by U, and d by d plus d by f. What we have done? We have multiplied both the sides by negative d. Why we have multiplied both the sides by negative d? Because upon multiplying both the sides by negative d, we get this expression here. And then in the next step, we can replace it by m, the magnification. Writing m for negative d by u, we get angular magnification when image is at a near point. This formula gives angular magnification when the image is formed at a distance of near point. This formula tells us the increase in the apparent size of an image compared to the apparent size of an object when it is viewed directly from the distance of near point, the closest distance for clear vision. Now image can be seen clearly at a distance of 25 centimeter. It is more comfortable to view the image from at infinity. Now we consider the case of image form at infinity. To form an image at infinity, again we have to adjust the position of an object. The appropriate distance of an object for the image to form at an infinity is obtained as follows. The image is to be formed at an infinity. So the image distance is negative infinity according to sign convention. Now we use thin length equation and find the appropriate distance for an object u by substituting the image distance of negative infinity. It is a simple calculation to substitute for negative infinity in place of v to obtain u equal to negative f, the focal length. To obtain angular magnification, again we calculate these angle subtended in the two cases, one without lens at a distance of 25 centimeter, another with lens. In this triangle, we can see that theta 0 is approximately equal to tan theta 0 when the angles are very small, and tan theta 0 may be written as the ratio of opposite side, which is h, by d. And now here in triangle A, B, C, this angle is also theta, and we can write theta equal to tan theta, and tan theta is equal to the opposite side divided by the object distance. But this adjacent side BC is negative of u because u itself is negative and the opposite side must be positive. So BC, this BC is equal to negative of u because u itself is negative, but BC have to be positive as it is the side of a triangle. So for BC, this adjacent side, we write negative u to make it positive. And now the formula for magnification is theta by theta 0. We substitute for theta in theta 0 and we get negative d by u. And now we substitute for u as negative f here and get this. This final formula represents magnification when the image is formed at infinity. Here we see that the magnification is smaller than in the case where the image was formed at a distance of 25 centimeter. For the image at near point, we had a magnification given by m equal to 1 plus d by f. For image at a near point, the magnification is greater than the magnification for image at an infinity. Means when this might be a disadvantage for viewing the image at infinity because the magnification is 1 less compared to the magnification when the image was formed at a distance of near point. However, the advantage of the image at infinity is that our eyes are considerably relaxed and comfortable in viewing these images. Please like, subscribe and share this video. Thank you for watching.